Simple high-gain array antenna for 5G applications. Ali Ahsan Hasnain Electrical. High-Tech University Taxila Kant Taxila, Pakistan. Abstract A 1x4 microstrip patch antenna array operated at 28 GHz covering 5G frequency band is proposed in the design. The Rogers RT/duroid 5880, TM, with a relative permittivity of 2.2, dielectric loss tangent 0.0009 is used as a substrate in the design with a thickness of H equals 0.787 mm. The single element patch antenna has a gain of 8.43 dB and a bandwidth of 2.54 GHz at 27.94 GHz. The array of the single element has a gain of 12.986 dB and a bandwidth of 3.07 GHz at 27.99 GHz. The maximum gain achieved by the antenna array is 13.04 dB at 27.8 GHz. Keywords: patch antenna array, 5G applications, gain enhancement. Introduction. In the era of modern communication, users need high data rate, smarter and efficient transmission of data in cellular industry. To achieve higher data rates and faster communication for the end users, the idea of 5th generation 5G came into being. It has several frequency bands to transmit and receive electromagnetic waves for 5G applications. The 5G network is faster in speed, which is 10 times the bit rate available today, and its coverage area is 1000 times greater than the 4G network one. The increasing numbers of users bring in a bandwidth scarcity, and to accommodate large end users there is a need of increasing bandwidth that increases the overall data rates of the system. The high data rate provides the end users with the faster and smarter communication. Many microstrip patch antenna arrays have been designed and investigated in recent years. A millimeter wave filtering monopulse antenna array based on substrate integrated waveguide, SIW, technology is proposed in 2 covering Ka band operated at 29.25 GHz with gain of 8.1 dB and bandwidth of 0.351 GHz. A 2x2 microstrip patch array antenna for 5G C-band access point applications with 2 vertical slots is designed 3, which is operated over 3.4, 3.6 GHz, with gain of 5.37 dB and bandwidth of 0.2 GHz. A dual-band millimeter wave microstrip patch antenna array is designed in 4. The antenna is operated at 28 GHz and 24.9 GHz with a gain of 8.42 dB, 5.375 dB, and bandwidth of 0.9 GHz, 0.3 GHz respectively, having applications in future 5G smartphones. A compact 4-element slotted antenna array is designed in 5 for 5G applications with a length of slot 4.01 mm having a maximum gain of 9.25 dB at 26.9 GHz and bandwidth of 1.27 GHz. A microstrip patch antenna array is designed using tapered line feeding in 6 for 5G mobile communications. The antenna resonates at 4 different frequencies: 23.2 GHz, 27.09 GHz, 31 GHz, and 42.5 GHz with bandwidth of 1.18 GHz, 1.63 GHz, 2.185. Muhammad Nauman, Muddasir Abbas, Muhammad Asad Anwar, Iftikhar Ahmed, Muhammad Talha. Asghar Electrical. High-Tech University Taxila, Pakistan. GHz, 2.43 GHz, and gain of 12.3 dB, 13.1 dB, 9.4 dB and 8 dB respectively. All the antennas reviewed so far are designed for the 5G communications, however these antennas have low value of gain and they have limited bandwidth. The proposed antenna has an array of 4 elements with a high impedance matching feeding network operated at 28 GHz that increases the gain and bandwidth. In this paper, a simple 1x4 microstrip patch antenna array is demonstrated which fulfills the basic needs of 5G communication system. The design of our antenna is discussed in Section 2. The results and parametric analysis are discussed in Section 3 and Section 4. In Section V, the conclusion of the paper is discussed. 2. Antenna design. The 1x4 microstrip patch antenna array of single patch element is designed in Fig 1. The designed antenna is covering the 5G band of communication and is operated at the 28 GHz. The prototype is designed on Rogers RT/duroid 5880, TM, substrate with relative permittivity of 2.2, dielectric loss tangent 0.0009 with height of 0.787 mm. The overall length of the proposed design is 20 mm and the overall width of the design is 57.4 mm. The feeding network is made up of multiple lines having the impedances of 50 ohm, 70 ohm, and 100 ohm that connect the individual antennas into a network. In this design, the patch has an input of 100 and must be matched to a transmission line of 50. There is a quarter wave transformer of 70 ohm in between 50 ohm line and patch used for impedance matching, and it also reduces the power losses. The dimensions for the feeding network are shown in Table I. The technique that is used to feed an antenna is power divide technique, in which the input is equally divided among all the patches. In Fig 1 the R equals 2.5 mm is truncating the 50 ohm line and is used for better impedance matching. Fig 2 shows the 100 ohm transmission line and patch that is connected to each other. The dimensions for the width and length of patches and transmission lines are shown in Table 2. By increasing value of R radius of truncation, as shown in Figure 2, resonance frequency shifts towards higher frequencies. At R equals 2.5 mm the antenna resonates at desired frequency of 27.99 GHz. Simulated S parameter at different values of R. 4 results. The simulated return loss, S11, of single patch element and its array is shown in Fig 5. The operational frequency of the single element is at 27.94 GHz having bandwidth of single patch antenna is 8.43 dB. The array of the single Table 3. Summary of related Revit works and are proposed. Patch element is used to increase the overall gain of the antenna that has several applications in cellular industries. V. Conclusion. A 1x4 antenna array for 5G applications is designed having a high gain of 12.986 dB. This high gain antenna radiates in the specific direction having many applications in cellular industry and is covering the 5G band, 27.19 GHz, 30.26 GHz. The bandwidth of the proposed antenna is 3.07 GHz with a return loss of -17.85 dB at 27.99 GHz. The array of single patch increases the overall gain of the antenna that makes it viable for cellular and wireless communication.